If you've been with us all year going through the assignments, we've seen this creature come up quite a bit. And perhaps we explained it a little bit earlier in the year, but for many of you, this may be the first time you're seeing this thing. And every time in our book that we saw it, the set of problems that had this limit equation in here would include a little symbol like that, which our book uses to tell us this is something you can expect to see a lot of in calculus. And you just get a lot of mechanical background on this before you ever learn what it is. So here we go, a debunking, an explanation of what this creature really is before we look at some problems in regards to it. Let's say we have a function, in this case f of x, and let's say the graph of that function ends up looking maybe something like this. So this is f of x equals y. And let's say we have a point on here, and any point on this function could be, given the ordered pair, some value of x produces some value of y. Now, if we were charged with finding the slope at this point right here, like our instantaneous slope, let's say that this is, let's say this in our graph, the x-axis represents hours, the y-axis represents miles traveled. Our slope, as you all know, is change of y over change of x, but our y values are miles, our x values are hours, miles divided by hours, miles per hour. Oh, so our slope actually has some meaning in the real world. So what the fact that we're flat here would indicate that we're traveling at 0 miles per hour. Now we're starting to speed up. And if I wanted to be able to look at this graph and figure out how fast are we going right at that instant, I need to find the slope at that point. Well, all we know about slope so far is that we can take a y coordinate minus another y coordinate and put it over the corresponding x coordinates, and that's our slope. The problem with that is I only have one coordinate, and I know if I choose another point on the line, say right here, I now have two coordinates, and I could go ahead and find the slope of those, but if it's not a straight line, I'm going to claim my speed in miles per hour at this point is faster than my speed back here. So what we'd want to do is choose points that just get increasingly closer to here and continue to find the slope. Okay, let's say this point that I created is over just a little bit, and I'm going to call this value h, not for hours, just h is our favorite variable for this type of problem, as you can see up here. I'm going to call that h. That would make this ordered pair become x and then h more to the right. The y coordinate would be f of that, f of x plus h. And then I could find the slope of the line, the straight line joining those 2 points, although I don't believe it is straight. I think there's a curve through there. But if we found that, we'd at least be somewhere in the ballpark of what our speed in miles per hour are right here. Our speed is. Okay, so that would be, take the first y coordinate, or a y coordinate, f of x plus h, minus the other y coordinate, f of x, and place that on the x coordinates, x plus h minus x, and we see that we get this creature up above, f of x plus h minus f of x on the x's cancel h. So there it is, but what is going to give us a more and more accurate representation of what's going on right here is to just continue to pull this point closer and closer and closer. Ideally, it would be the same, which would make our value of h be 0. We would have, let's suggest for a second that this ordered pair right here actually turns out to be 4, 2. And if I use just the 0.42 and the 0.42 again, my slope would be 2 minus 2 on 4 minus 4. Yikes. We just crossed the beams 0 on 0. But I'd like H to be 0. I'd like to get 2 points close together, and that's where we get this statement. We want the limit as H gets as close as we can get to 0. So that is where this guy comes from, and we have seen a lot of this year, and you're going to see a little bit more before we get you into some really cool shortcuts soon.